you recall, in the last lecture we had talked about the various logic gates. Now, in the present lecture we shall be talking about some logic families to implement gates. Now, what do we mean by logic families? See, over the years there have been many techniques or many ways in which people have come up with for designing these basic gates, because the ultimate objective was to design circuits, digital circuits, and these gates were the basic building block. Now, we shall be looking at some of these techniques or logic families using which such gates can be constructed, which will help us in designing larger circuits. Now, we shall be looking at some of the conventional methods which have been used and also some unconventional methods. So, this we shall be discussing in the next couple of lectures. So, today in this lecture we shall be talking about the issue of logic families, which means how to construct logic gates, so that they may be used in circuits. Now, when we talk about logic families, there are various logic families which have been used, like conventionally there are techniques like diode transistor logic, transistor logic, emitter coupled logic. Today the most widely used is something called CMOS, complementary metal oxide semiconductor. This is universally used today, and there are some unconventional families also, which we shall also be discussing in the next lectures. Just let me tell you, unconventional, it can mean some kind of optical circuits, where instead of voltages and currents we talk about lights, presence and absence of lights, or there are something called resistive circuits, where the resistance value of some devices change, and that can represent the state 0 and 1. Okay. But in this lecture we shall be looking at some of the more conventional logic families and how they work very briefly. We start with diode transistor logic, which was one of the first logic families that were proposed. So, as the name implies, we use semiconductor diodes and transistors. So, when this logic family was proposed, bipolar transistors were used for the implementation. So, I am showing you some simple examples. Let us consider this case where we want to build a 2 input AND gate. So, the way this circuit was designed was like this. There were 2 diodes connected like this, and on the output side there was a resistance connected to a positive supply voltage. Now, let us see how this method used to work. So, the inputs are A and B. Suppose I have grounded both the inputs. Ground means, let us say, logic 0, and this positive supply voltage means logic 1. Let us follow this convention. So, if the inputs are at ground, then you see from this power supply there will be a current flowing path, current will be flowing towards A and B, and the voltage at the output node will be very low. It will be ground plus the drop across the diode, maybe about 0.6, 0.7 volt, like that. So, the output will be at a very low voltage, and that very low voltage, let us say it is equivalent to logic 0. This will be true if at least one of the inputs are ground. If A is ground, B can be high voltage also, or B is ground, A can be high voltage also, then also there will be a current flowing path and the same thing will happen, output will be 0. But if both the inputs are at the high voltage plus voltage, then the diodes will be reverse biased, no current is flowing, and the output will be equal to VCC. So, the output will be 1. So, you see this is the truth table of an AND gate. So, you can realize an AND gate like this. And just a thing, if you just reverse the direction of these diodes, if you connect them like this, then it becomes an OR gate. OR gate says if at least one of the inputs are 1, then one of the diode will be forward biased, there will be high voltage here and the output will be high. But if both of them are 0, then this will be forward biased, the voltage here will be 0. So, this you can design like this. And to build a NAND gate, for example, you have already seen how to build an AND gate. This AND followed by a transistor circuit like this. This realizes a NOT, and AND followed by a NOT is an AND. You see this transistor how it works. If this voltage is 0, low, this transistor will be off, no current will be flowing and the output will be almost equal to VCC high. But if this is 1, then the transistor will be conducting, there will be a current flowing and the output will be almost connected to ground, it will be 0. So, this will be a NOT operation. If it is 1, it is 0, if it is 0, it is 1. So, this is NAND. So, in diode transistor logic, used to use diode and transistors like this to build circuits. Then came transistor logic, where diodes were replaced by transistor, which made it switch faster. See, I am not going into detail of the explanation. This is the circuit diagram of a 2 input NOR, this is the circuit diagram of a 2 input NAND. Let us say NAND gate. So, whenever at least one of the inputs are at 0. So, this emitter, multi emitter transistor, this emitter would be conducting, this would force this transistor to be off, and then it would force this transistor to be conducting, and VCC will come to the output, output will become 1. So, this is roughly how it used to work. I am not going into detail operation of this, but I am just showing that in TTL there were so many resistances and transistors, bipolar transistors, that are used to realize the basic gates. Okay. These TTLs were used for SSI and MSI level logic at one point in time, but today you do not see this kind of circuits anymore. Okay. Today, as I said, that most of the circuits we see is based on the CMOS technology, and CMOS technology is designed based on the premise of a switch, electronic switch, a switch closing and a switch opening. Let us try to understand the concept. So, so-called switch based circuits, they rely on the operation of miniature switches, tiny switches. Switches can be in two states, they are either open or closed. So, you know how a switch is. So, equivalently I am showing a bulb connected in a circuit with a power supply and a switch. So, if this switch is open, no current is flowing, bulb is not glowing, but if the switch is closed, current will flow and the bulb will glow. So, you see in this kind of switch based circuits, there can be distinctly two states, switch open state and switch closed state. So, in one state current is flowing and the light is current is not flowing and the light is not glowing off. In the other state current is flowing and the light is on, right. Okay. So, let us from here let us now look at some relevant issues when we are trying to design gates. Let us consider, suppose we are trying to design a gate, let us say an AND gate. So, we are applying some input, So, inputs are typically in the form of voltages, but in digital domain in binary we say it is 0 or 1, and the output will be something, it will be 0 for an AND gate. Now, when I say 0 or a 1, what does that mean? 0 can mean it is a low voltage, 1 can mean it is a high voltage. But well, you may ask, this low and high are very subjective terms. How low or how high? So, how low the voltage should be so that the gate can treat the input as 0, and how high the input should be, the voltage, so that the gate treats the input as 1. These are some issues that need to be talked about. So, we are talking about something called voltage ranges and noise margins. So, as I just now said with this example, a range of voltages is treated as logic 0, while some other range is treated as logic, sorry, this should be 1, logic 1. Now, the exact range of voltages, it of course will depend on the logic family, what kind of logic family you are using, and for reliable operation there should be sufficient margin between the two levels, because your electronic circuits are never perfect. There will be some small variations in their operation and performance. So, if your logic 0 and logic 1 are sufficiently spaced, there is a lot of gap in between, then even in the presence of small variations in performance and the parameters, the circuits will continue to work correctly. Okay. So, you see here I am showing an example, which is an example that pertain to the TTL family, transistor logic. Here the digital values 0 and 1 are represented by the voltage range 0 to 0.8 volts and 2 volts and above. These are the ranges of voltages to represent 0 and 1, and whatever is there in between greater than 0.8 volt and less than 2.0 volt, this is considered as an invalid voltage range, and this is the so called noise margin. Okay. Because of some external noise, a 0 should not become 1 or 1 should not become 0. There should be sufficient gap in between, and this noise margin, this ensures that. Let us now come to slowly towards CMOS, complementary MOS. So, in CMOS we have two types of transistors, N type and P type. Without going into the detail, just look at the functionality. We have N type and P type transistors. So, when you talk about N type metal oxide semiconductor or MOS transistor, the schematic diagram is like this. This is how the transistor looks like. There are 3 terminals, gate, and the other 2 terminals are called source and drain. So, when we apply a positive voltage on the gate, the switch is closed like is shown in this diagram. The switch is closed, this is the equivalent circuit, and between points 1 and 2 there can be a current flowing. But if gate is 0 voltage, the second scenario, this transistor will be non-conducting and there will be no current between 1 and 2. So, equivalently I can say that this switch has become open. So, for N type MOS transistor, when you apply gate 1, 1 means high voltage, switch is closed. If we apply 0, switch is open. But for P type transistor, the situation is exactly reverse. For a P type transistor, which is represented like this, there is a small bubble here, this indicates P type. Here when the well here the positive voltage can be anything, here I am showing us plus 2.9, it can be higher also, 5 volts also. So, here if the gate is low voltage 0, then it is conducting, but if the gate is high, then it is non-conducting. So, the behavior of the switch is just reverse. If the gate has positive voltage, switch is open. If the gate has 0 voltage, the first one, the switch is closed. right. So, the behavior of the p type and n type transistors are reverse with respect to the switching behavior. Now, let us come to CMOS circuits. So, how a CMOS gate is built? So, let us come to the simplest circuit. We show a CMOS NOT gate. So, here the input is in the diagram, the output is out. So, the truth table will be like this for a NOT gate, 0 will become 1, 1 will become 0. Let us see how this circuit works. You see, there are two transistors that are connected, one is a N type transistor, other is a P type transistor. Let us call them T1 and T2. Let us suppose my input voltage is 0, that means low voltage. So, for input voltage 0, what we have seen, the N type transistors would be off and a switch will be open, and P type transistor it will be on. So, T1 will be on and T2 will be off. So, what does this mean? T2 is off means from out to ground there is no connection, it is off, but this is on means plus V is connected to the output, which means output will be high voltage, that is why output is 1. But if your in is 0, in is 1, now the reverse will happen, your T1 will become off and T2 will become on. Because T2 is on, now out will be connected to ground, it will be low voltage, so it will be 0. So, it works as a NOT gate. This is how a CMOS NOT gate works. Okay. So, other kind of gates are also fairly easy to build. Let us say a NAND gate. NAND gate will require 4 transistors as we show in this diagram, 2 N type transistors here and 2 P type transistors here. This is the truth table. So, when let us consider this last row first, when both the inputs are 1 and 1, then what will happen? Both these pull down transistors will be on and these will be off. Because these are on, from the output to ground there will be a path. So, output will become 0, output will become 0, right. But if we consider any of the other scenarios 0 0, 0 1 or 1 0, here at least one of these two transistors will be off, let us say B. So, one of them will be off and at least one of these two transistors will be on. So, because one of A and B are off, one of them is 0 at least. So, from output to ground there will be no path, but because at least one of these two transistors is on, from plus V to out there is a path. So, output will be high, so output will become 1. This is your NAND function, right. So, this is how this NAND gate works in CMOS. NOR gate operation is similar, just the structure of the circuit will be a little different. It will look like this. So, this P type transistors are coming in series and N type transistors are coming in parallel. So, here again you see when both the inputs are 0, 0 means what? This is off, this is off, both these are on, this is on, this is on. So, from output to ground there is no path, but from plus V to output there is a path. So, output will be 1, output is 1. But for any other condition you can check at least one of these two N type transistors would be on, because one of them is 1. So, output to ground there will be a path, output will be low, and both these transistors are not on. So, plus V to out there is no path. So, this is NOR operation. Okay. So, it is easy to verify that it works. So, here I am assuming these transistors to be just switches. I am not looking into the other electronic characteristics of the MOS transistors, just functionally how it works as a gate. Okay. Now, when you want to design the other type of gates, for example, AND, well, in CMOS you cannot directly implement an AND gate. So, what you have to do? You have to first implement a NAND gate followed by a NOT gate. So, in CMOS, you remember, in CMOS it is much easier to design a NAND gate, more difficult to design a NOT gate, more difficult to design an AND gate. You see, this is an AND, because what you have done, a NAND followed by NAND means what? AND followed by NOT, two NOT one after the other, they cancel each other, it becomes AND. Okay. So, CMOS AND gate will be one NAND gate followed by a NOT gate. Similarly, OR gate. So, OR gate will be NOR gate followed by a NOT gate. So, there will be a NOR gate followed by a NOT gate. This is OR. Now, this concept can be extended to any number of inputs. You can see, instead of 2 transistors CD, you can connect many of them in parallel. Instead of CD, you can connect many of them in series. So, you can have a multi input NOR gate, similarly NAND. Okay. So, here I have not gone into the detail of CMOS designs, but just giving you some idea that in CMOS how you can build gates, and the advantage of CMOS is that in modern day technology you can build these CMOS transistors, or you can manufacture this CMOS transistor in a very small dimension, because of which in a chip you can pack so many gates today. You can pack close to 1 billion of transistors and gates in a chip. So, CMOS gives you that big advantage, and in CMOS design you do not need any resistances and any other components, diodes, these kind of things are not required, because resistances typically require much more area to fabricate in a chip. Here you need only the transistors. Okay. So, with this we come to the end of this lecture, where we had a look at some of the logic families. In the next lecture we shall be continuing a little bit more on CMOS, and then we shall be talking about a couple of unconventional technologies. These technologies are coming up, they can also be used to design digital circuits and gates, and we shall be looking at those things. Thank you.